I'm a writer for the Yale Scientific Magazine, and I'm here to talk about the Kepler-36 system with Professor of Astronomy Sarvani Basu. So, Professor Basu, can you just briefly introduce yourself first?
As Lee said, I'm a professor in the astronomy department. I've been at Yale since 2000. And my basic research is on stellar astrophysics. I spend roughly half my time studying the sun and the timescales over which the sun changes and which can affect life on Earth, and the other half I spent studying other stars, and these days in particular I'm studying the host stars of exoplanets, which is how I got involved in this project.
Professor Basu actually just co-authored a paper on the Kepler-36 system, which is very interesting because both of the planets have vastly different compositions and natures. Can you just tell us more about how you got started on this project?
Josh Carter, who's the lead author, he found these two planets and realized they were somewhat weird. And luckily, the rest of us found is that the star around which the planets are orbiting, the star shows pulsations. And the nice thing about stellar pulsations is that way you can figure out what the mass of the star is, that is how heavy it is. It's about the only way you can find the mass of a star which is not in a binary system, and also how big it is. So Kepler planetary data can tell you how big a planet is with respect to its star, but it cannot tell you how big a planet really is till you know how big the star is. So what my role was in the analysis of the pulsational data to figure out how big the star is and how old it is. It actually turns out to be much older than the sun. Slightly bigger than the sun, but it's quite a bit older than the sun, and it's a dead star in the sense unlike the sun, it has exhausted all hydrogen fuel in the core. Mm-hmm. So it started from there. So once we gave Josh and his group, his planetary group, the data from the stars, from the analysis of the star, then he could go ahead and figure out how big the planets were. Mm-hmm. And that's when he did further analysis to figure out how heavy the planets were. So once we know how big they are and how heavy they are, you can roughly guess what its composition is going to be. Mm-hmm. So the smaller star is actually quite a bit denser than the Earth. So it has to be rocks and heavy elements. Mm-hmm. The smaller planet, sorry. The bigger planet is less dense than Jupiter. So it has to be a gas giant. The question, of course, is exactly what the composition is, etc. Those are going to be the interesting questions which people might need to look at.
Wow, so how do you think that these two planets, these vastly different planets, came to coexist in the same system?
They couldn't have been formed there. Mm-hmm. So the most likely scenario is that the bigger planet was formed somewhere else and it migrated inwards. That's the common way we expect large planets very close to their star are formed. I mean, if you look at Jupiter, it's way farther away from the sun than Mercury is or the Earth is. And in fact, for a long time, before we had seen planets around other stars, people had thought that you can't have gas giants like Jupiter or Saturn close to a star. But the first extrasolar planet that was discovered turned out to be a Jupiter-like star, Jupiter-like planet, closer to its star than Mercury is. So that's when people who study how planets are formed started looking at how it is possible to have a Jupiter-like planet close to a star. And the current view is that you form them far away, and then they slowly move in under different influence. But what to me more interesting is not just that they're so close together, that of course could be chance, but how different they are in composition. Mm-hmm. We know Jupiter is different from the Earth in composition, but still this difference is magnified in these two stars. Mm-hmm. it's also a cool system in the sense that the planets now are so close together. It's like the Earth-Moon system where the Earth affects the moons through tides and the moon affects the Earth through tides. Here the tidal forces would be immense because the big planet is so close to the small one. So the small one, you could easily have things like earthquakes and volcanic activity because it's being constantly tidally disturbed by the large planet.
I see.
So that's the fun part too. The fact that it's really an alien world. We don't see any counterpart in the solar system.
Yeah, were there some major challenges in the project?
No, in that sense it was quite well, from the stellar physics point of view, no. So the part which I was involved in. In the planetary part, yes. Because the small planet is so small, it didn't leave much of a signature in the amount of light it blocked from the star. So the larger planet was found first. So Kepler, it's observing hundreds of thousands of stars at any given time, so the data is processed in an automatic manner. The thing about automatic processing is it's only as good as the code that somebody has written. And with the smaller planet, it was really rejected by the automatic code. But then Josh Carter went in after he found the larger one and saw that there is a signature for a smaller planet, so he had to do a different type of analysis to get the smaller planet. So in that sense, that was a trickier analysis. The stellar astrophysics part was actually a reasonably easy one.
Did you have to go in and manually analyze it or use different software?
He had to, yes. So Josh was using Josh, and he collaborated with, I'm forgetting his name. I'm sorry, I have to look it up. Eric, I remember the first name. Professor Eric Egal from the University of Washington. So what they do is look at the fact that when you have, see, normally we think of a planet having a very precise period around its star. Okay, big around in 1 year around the sun. But if you have a close-by heavy planet, because it has its own gravitational field, it can change slightly the period of the other planet around its star. So in other words, the star doesn't have a well-determined period. So the period changes slightly. So this is what's called, in technical terms, a transit timing variation, meaning when you see the planet in front of the star, that'll change slightly. And so there are ways to do the analysis of that, and they use this transit timing variations to actually study this planetary system.
Did your research objectives change significantly during the course of the project? Or,
Not during the course of the project, but they changed the moment Kepler started giving data, because we realized that yes, the main mission of Kepler is to look at planets around other stars. But the same data could be analyzed in a different way to study the stars around which these planets go. So we could tell you about we could help study the entire planetary system and not just the planets. So it tells us, so once we know, we can find, if we have enough data, we can find the age of the star. That gives us the age of the planetary system. Okay. And we're also looking at stars which don't have planets around them to study stars. And whether or not, even though stellar astrophysics is one of the more established fields of astrophysics, one of the problems with stellar astrophysics theory is that we cannot yet predict how big a star would be. There are uncertainties in the theory, particularly related to how energy is transported in cool stars and the cooler layer of stars. So that changes depending on how you treat that. That changes the radius, the predicted radius. So what these data allow us to do is actually measure the radii of stars. Before this, you could only measure the radii of stars that were very close by and very big and bright. But now we have a whole slew of stars for which we can measure the radius, which we can measure the mass. So we can now go back to a theory and figure out, so can we make the uncertain part more more certain. So that is what interests me. So my interest in the stellar astrophysics. And the other reason I'm interested is my basic research interest over the last 15 years has been the sun. But we know what the sun is like today. It's one point in time. To be able to know what the sun was like in the past or in the future, at the moment we have to rely on our theory. Okay. It's a reasonably good theory, but it's only been tested at one point of time. So with all the Kepler data, what we can do is look at other stars that are very similar to the sun and use those to inform our knowledge of the sun. So, for example, most properties of a star are determined by how heavy they are and how metal rich they are, how much iron is there, how much oxygen is there, and but oxygen in astronomy is classified as a metal. Anything heavier than helium is classified as a metal. So the metallicity of a star, that is how much elements heavier than helium is there in a star, and the mass of the star basically determine the stellar properties. So if we can find stars that are very similar to the sun, but of different ages, it tells us what the sun could have been like in the past, what would be like in the future. One of the reasons we want to do this is something which some people call the faint sun paradox. When the sun was young, that is when about 4 billion years ago, when life was just supposed to have been formed on Earth, the sun was actually only 70% as bright as it is today. So if you look at the energy output from the sun, then the Earth's oceans should have been frozen. Okay, so the question is, they obviously weren't, otherwise we couldn't have formed them. All the evidence points to the fact that they weren't. So there are two hypotheses. One is that the early Earth was warm because of greenhouse gases. That was a time of large volcanic activity, and a lot of gases were spewed out. The other hypothesis is that the sun was actually formed heavier than it is today. Heavier stars are brighter, and that the sun lost a lot of mass while it was evolving. Now, whether or not it did so, we can only test if we find stars that are young, that are losing a lot of mass. If we find those stars, then we can say, yes, it's a likely scenario. If we find young stars which are somewhat heavier than the sun, but they don't seem to show any mass loss, then we'd say, no, that scenario is unlikely. But these are observations that are difficult, so which is why my view is looking at these stars and figuring out how old they are, what are their properties, and then see if any of them is anything remotely like the sun, so that I can connect it back to my solar physics research.
Also, just what were the really pivotal moments during the project, in your opinion, or major breakthroughs?
The pivotal moment, I think, was basically when Josh Carter and Eric figured out that they have two very different sized planets around this star, but they had no idea how big they are. And we needed to know what the star is like to answer that question. So that's when we actually started looking at the system as a whole, rather than, hey, we've seen two more exosolar planets. By now, the number of exosolar planets has grown enough that just discovering one is no longer news. Okay. What's interesting here is, of course, it's so different. And that's the interesting part.
What do you think the major implications or takeaways are of this project?
The major implication, to my mind, which I try to tell my students, is never believe in automated pipelines. Nothing can substitute for the human eye. If Josh hadn't looked at this system by eye, we wouldn't have known that there's the second planet sitting there. yes, automated, you require automated pipelines, but at some point you need to go and look yourself. Nothing beats actually paying attention. Computers are very good, but they're only good to a certain extent.
Mm-hmm.
They allow you to do things fast, but nothing stops. But they can't pick up patterns which they're not meant to pick up.
Mm-hmm.
And that's where all the interesting stuff, particularly in this planetary system, that's where the